This video is just more practice with identities, more practice with double angle formulas, nothing new, just new problems. How to choose which double angle formula you're going to use for this identity, and remembering how to verify identities as well. Again, there is no answer necessarily. There's nothing really to box when we're verifying identities. It's all about the process. It's all about how we formulate our work. Our answer is the entire proof, if you will. Example 4. Already on example 4, just on the second video. Verify the following identities. Part A. 1 plus the sine of 2 times any angle is equal to the sine of that angle plus the cosine of that angle, and then square it. So one of our rules of thumb with verifying identities is to start with the more complicated side. In this one, it's up for interpretation. I think there's a little bit more to do with the right-hand side, but the left-hand side has that double angle formula just waiting to be used. So again, you can start with either one. You can do both, but if you do both, you have to do them separately. Don't start with what you're trying to prove. If you'd like, right, you can work with the left-hand side at the same time that you work with the right-hand side. You just have to do it like this in parallel. And then hopefully, you know, we do little trails with the left and the right, and then pink, they end up meeting in the middle. That would be great. All right. So the left-hand side is 1 plus sine of 2 theta. We can use the double angle formula. The sine of double an angle is 2 sine of that single angle times the cosine of that single angle. And now we're kind of stuck. You know, I know where to go from here, but I certainly don't think it's obvious. So we use the double angle formula and we said, I don't know what else to do. Maybe you see it too, in which case great. But if you don't see it, there's two options. When you're verifying identities, if you get stuck like this and you don't see what to do next, maybe you made a mistake. You can go back, double check your answer. We've only done one thing, so that shouldn't take very long. And the second thing is, well, maybe go to the other side and see if we can work with the other side and make it look more like the left. So for the right-hand side, be very careful. Right, that's the sine of theta plus the cosine of theta squared means multiplied by itself. You can't just square things individually. You have to FOIL it all out. First, outer, inner, last. And if you use the foiling shortcut, you should get that. This is the sine squared of theta plus 2 times the sine of theta cosine theta plus the cosine of theta squared. Oh, now we see the relationship between the left and the right. Right, both of these have this term. The only difference is one has a 1 and one has a sine squared theta plus cosine squared of theta. But we know what this equals. The Pythagorean identity says these green guys add up to 1. So this is indeed 1 plus 2 sine of theta cosine of theta, which is again equal to the left-hand side. Zoop. Check. Double check. Smiley face. All right, so again, how we've written this proof shows everything. We start with the left-hand side. We showed the left-hand side equals something. Then we went to the right-hand side and showed that the right-hand side equals the same thing that we showed that left-hand side equal to. So they are connected. Even though we didn't go left to right, we went left to a little bit and then right to where we got to. Right? It's like if you're digging a path underground, digging a tunnel. It doesn't matter if you dig the whole tunnel from one side or dig a little bit from one side and then go to the other side and dig a tunnel, as long as that tunnel meets. If that tunnel doesn't meet, you got no tunnel. Okay. There we go. Part B, verify this. The tangent of 2 theta equals 2 divided by the cotangent of theta minus the tangent of theta. This is really another example of that same phenomenon, that the right-hand side's messier. The right-hand side has more that we can do with it. but the left-hand side has the double angle formula. So I would probably recommend the same strategy that we did in the last one. But again, you really can start with any side here and just go all the way. The question is just, do you see it? And that's the thing. That's why identities can be such a struggle, is because there's no single method that always works. It's just about problem solving. It's about, what do you see? What strategies do you have available to you? How can you figure it out? Because you're never going to be able to know all of them. Even me, when I do these problems, most of these problems I haven't seen before or haven't seen in a really long time, but I've just done so many that I know good ideas, good things to look for. And that's, as you get more practice, is where you're going to get. So let's do a little bit with the left-hand side. Let's use that double angle formula. The tangent of 2 theta is, I believe, 2 tangent of theta divided by 1 minus tangent squared of theta. And now we have 2 options here. 2 options. If you don't see where to go from here, then you can work with the right-hand side. Simplify the right-hand side, specifically reciprocal identities. Reciprocal functions. We usually want to get rid of those. So you could work with the right-hand side, get rid of that reciprocal. We usually like to put things in terms of sines and cosines, but that doesn't really make sense as a strategy here because both sides have tangents. It's still valid, and it still would work to put things in sines and cosines, but I wouldn't recommend it. That's why it's a rule of thumb, not a rule of iron. I don't know. I don't know what. It's a rule of thumb is like a good idea, but it's not like you always do this. Okay. Another strategy that is always good to remember is when you're verifying identities, look at where you want to go and look at where you are. What's the relationship between these 2 things? What's the relationship between our 2 numerators? Our numerator has a tangent. Our end result doesn't have a tangent. We could divide everything by tangent. If we divided the top and the bottom by tangent, that would make the numerators equal. What happens if we divide the bottom by tangent? Let's find out. Let's divide the top by tangent of theta, and let's divide the bottom by tangent of theta. Oops. If we do that, then the top, the tangents cancel, and the bottom we have 1 over tangent theta, and then one of the tangents is going to cancel. Okay, we're basically there, right? The 2's match, the tangents match, and cotangent is the reciprocal of tangent. So we have 2 divided by cotangent of theta minus the tangent of theta, which is the right-hand side. Check, check, smiley face. All right, we did it. We showed that one side is equal to the other. We verified that this is indeed an identity. You could graph both of these equations, both sides, and you would get the same function. The same graph, rather. Outside of any weirdness with dividing by 0 arrows. Their domains might not always be the same, actually. So I should be careful when I say the functions are the same, because functions are only the same if their domains are the same as well. But that's splitting hairs, and it's important hairs that we're splitting, but I don't think it's ideal to get hair splitting to get in the way of learning. Anyway, that's this video. Good luck. Verify some identities for me. And when we come back, we'll talk about reduction formulas, how to make exponents disappear. Bye-bye.